Hi, we are here again with an energy brief, this time with Dr. David Tu. We're going to be talking about a key program that he's running in the machine learning space called Differentiate. Dave, how are you doing today?
Doing pretty well. How are you, Rakesh?
Doing great. So let's get into the questions here. The first question I had was, what's the basis and hypothesis around the Differentiate program and how has it been structured?
Well, the motivation of the Differentiate program is to develop machine learning enhanced design tools that will hopefully enable energy engineers to be more productive, to enable them to design better energy products faster to help us address our climate and energy challenges going forward. The program was structured largely around kind of the nominal engineering design process or scientific method, where engineers hypothesize new design concepts, potential solutions to problems. Then they evaluate those concepts and see how they perform versus their target performance metrics. If they don't get it right the first time, which we never really do, then we go and iterate. So we're developing tools to really help engineers take better guesses faster. Really, these come down to better optimizers that may employ techniques like reinforcement learning. We're then developing machine learning based surrogate models, which help engineers make relatively high fidelity performance predictions of their design concepts at lower cost than they could otherwise, which helps them basically close the loop and iterate much faster to hopefully yield an optimal design or an engineering optimal design for their target problem. In some applications, we're actually taking advantage of a general characteristic of deep neural networks that enables them to be very good general approximators to any function. And so what we're trying to do is actually express designs as functions of requirements, so that basically given a requirement, we can have, in theory, a deep neural network that actually just gives us a design candidate. And we're pursuing this inverse design process, the so-called inverse design process for photonic problems, as well as aerodynamic problems, and actually the design of heat exchangers as well. And I'm actually very excited by its potential going forward in terms of in terms of its potential to lower the cost of, let's say, custom designs in a range of applications.
So you touched on this briefly in the previous. So roughly, how have you organized some of the technical domains that were the focus for the development of the machine learning tools, and what are some of the key highlight accomplishments that you've seen to date from the teams?
Well, I guess early on we decided it would really help teams accelerate the development of their tools by encouraging them to focus on specific energy challenge problem areas, which are really of interest to ARPA-E. And then the hope is that these tools that they develop are somewhat general purpose, and they can take them from the energy challenge problem area they're working on to some other energy challenge problem. The energy challenge problem areas we're pursuing within the program include system architecture designs for electrical circuits as well as thermodynamic systems. We're also trying to design molecules for various applications. We're also trying to develop materials in a range of applications. Catalysts in particular are a common theme through at least 3 of the Differentiate projects. We're also looking at aerodynamic surfaces as well as heat exchangers, and actually even trying to design aerodynamic or gas turbine compressors more efficiently. So really a range of energy challenge problem areas, kind of across the board. So I guess given the wide range of things that we're doing, Rakesh, how well do you think our Differentiate teams are posed for commercial success?
I think there are certainly some very interesting and exciting developments that have come out of the portfolio. There is a fair bit of additional work to be done. The nominal way in which that work will be done is through intense collaboration with their prospective customers and or strategic partners who are actually developing these new products or materials in the specific technical domains of interest and in the specific industries as well. But overall, I think the bottom line value proposition on this is, the acceleration of the product development timelines in terms of how quickly you get new energy products into the field is pretty exciting. And I think there is clear cost savings for folks who can kind of master the space. The secondary benefits is a lot of times just running experiments or even running computational models, which are sophisticated physics-based models, can be energy hogs, right? Because you're using these massive compute resources to solve the problems. And I think there is also an energy angle to the acceleration of the tools and the computational tools in terms of how they develop new products and or processes. So with that, Dave, one of the last questions I had was, clearly there's a lot more to do. So what are your thoughts in terms of some of the additional areas where ARPA-E could continue to make some investments to progress and advance this nascent field?
Well, I think, as you suggested, we're just really scratching the surface of the potential of these machine learning methods to really transform the way engineers design new products. I think there's substantial additional algorithm development we can do, even within the challenge problem areas that we're working on. I think we can look at how we actually take some of these tools we've developed in one application and move them into another application. I'd say one of the downsides to these machine learning based methods is the fact that you actually have to train the algorithms, of course, which requires substantial amounts of data, and that data frequently comes at high cost. But there are techniques actually to reduce the amount of training data that's required, potentially in subsequent applications when you've got maybe a network that can design a better compressor blade. Well, actually, there are a lot of similarities when it comes to designing turbine blades, and there may be a way to transfer information from the compressor neural network to the turbine neural network that lowers the cost, lowers the amount of data that is required to train the turbine neural network, for example. So I think lowering the cost of training data, I think, will be an important theme in follow-on differentiate-like programs, if there is such a thing at ARPA-E. But also there's tremendous opportunity in things like differential programming, looking at ways to try and leverage some of the discoveries that have been made regarding kind of similarities between differential equations and neural networks, and actually using neural networks to express the solutions of partial differential equations offers tremendous promise and tremendous potential to really lower the cost of evaluating the solutions to those partial differential equations. So I'm excited about where we can go from here, as well as some of the progress that we've made so far today.
And as always, we are interested in hearing from the broader audience in terms of additional areas where they think we should make investments in, and we'll be happy to listen and hopefully move and progress this area further. So with that, thanks again, Dave, for your time, and have a great day.
Great. Thanks, Rakesh.